to finish lesson 1.5 up, we have to talk about inverse relations and functions. So I think I talked yesterday briefly at the end about inverses. If you remember doing inverses from Algebra 2, maybe even Algebra 1, when you're trying to find an inverse, we take x and we take y and we switch them. Okay? So that's a lot of what we're looking at today. So a couple of key things before we actually go to some examples on the back. First of all, inverse relations. If an ordered pair AB, so A comma B is part of a relation, then the ordered pair BA is in the inverse. So notice that's just like taking X and Y and switching it. So if AB is in the relation, then switch it. BA is in the inverse relation. We're also going to talk about how to know if a function has an inverse. And so notice it says here, if a function has an inverse, then it will pass what is called the horizontal line test. Okay? We have the vertical line test, and the vertical line test tells us if something is a function. The horizontal line test tells us if an inverse exists for a certain relation. Okay? It works the same way. So, key definition here. Functions that have inverses are called one-to-one. So notice what it says. Functions that have inverses. Well, how do I tell if something is a function? How do we tell if something's a function? Okay, it passes the vertical line test. Okay. How do we tell if something has an inverse? Passes the horizontal line test. So how are we going to tell if something is one-to-one? It's going to have to pass both. Okay, so I'm going to write that in right here. So if it's one-to-one there, so it passes both vertical and horizontal, line test. And we will talk about that in some examples on the other side. A little bit of notation. The inverse of a function, f of x, we normally use f of x for a function. Inverse is f inverse x, so we write with that -1 exponent there in between the f and x, that's f inverse x. And then lastly, I already mentioned this once, but to find an inverse function, you switch x and y. So switch x and y, and then you are solving for y. I know we did that in Algebra 2, maybe even Algebra 1 also. Not exactly sure there. So switch to find an inverse, switch x and y, and then solve for y. Ready to do some examples? Okay, so we have 4 graphs up here, and for each of these 4 graphs, we have 2 questions to answer. For each of the graphs, we're going to ask, first of all, A, are the relations functions? So how are we going to be able to decide if they are functions? Okay, that will be the vertical line test. And then also for each graph, we're going to have a part B. And part B, we're going to have to determine if each of these relations has an inverse. How do we determine if it has an inverse? Horizontal. Okay, so if you would, graph A, as I said, 2 questions here. Graph A, question A. Is this an example of a function? Yes. Yes, because if it's a function, it passes the vertical line test. Okay. Part B. Is this, and so we know it's a function, does this function have an inverse? Yeah. Yes, how do we know? Now you get to say passes the horizontal line test. So yes, this is a function. Yes, this has an inverse. What's the special word I can use to describe this then? One-to-one. And I'm just going to write that in there so you have that as an example. But because it's a function and passes, and it has an inverse, it is 1-to-1. Okay, you ready for graph B? So question A, is this graph an example of a function? No, because fails the vertical line test. So no, it's not a function. Okay, so does this relation have an inverse?
Yes.
Yes? Okay, and that's because it passes the horizontal line test. Do you guys realize what's happening here? That these graphs are not going to extend and overlap each other because there's horizontal asymptotes happening is what's going on there. So the horizontal asymptotes are kind of running along there, and all the graphs are fine otherwise. So yes, it has an inverse. Graph C? So is it a function? No, because fails the vertical line test. Does this relation have an inverse? No, because fails the horizontal line test. That was a pretty easy one, right? And D. Is this graph an example of a function? Yes, because? Yeah, passes the horizontal line test. I know my morning class questioned, is this a parabola? And I said, yes, it is a parabola, but not in the true sense of a parabola, because if it's a parabola, what do we know about parabola? It's continually going out, and if that's the case, it would end up overlapping with these. But this is an idea where there are vertical asymptotes happening there that allow them to not overlap. So, yes, it is a function. B, is it, or does it have an inverse? No, because it fails the horizontal line test. So is it 1-to-1? No. The only one that was 1-to-1 was the first one. Okay, questions on that section? Okay, let's move to example 4 then. We're probably only going to do, I'm guessing, parts A and B here. This is what you did back in Algebra 1. Or excuse me, maybe Algebra 1, definitely Algebra 2, where you had to find the inverse of a function. How did it say to find an inverse? What did it say on the front page? Switch x and y. So now, when I go to switch x and y, first of all, do I have a y?
No.
Okay. Yes and no. There's no y staring at me, but what's taking the place of y? F of x. So realize that this actually says y equals x over x plus 1. Does that make sense if I say that? So now, to actually find the inverse, we're going to switch. Every place you see an x, replace it with y. Every place you see a y, replace it with x. So instead of y equals, I'm going to write x equals. Instead of x over, it's going to be y over. Instead of x plus 1, y plus 1. So the step I took there was to switch x and y. And then what do we need to do after we switch x and y? Take this equation and solve for y. Sometimes that's the easy part, sometimes that's the difficult part. In this case, I'm going with this is a little bit more difficult example. And I say that because we have y in the numerator and y in the denominator. So 2 different places there. Thoughts on where to start on this one?
You take x, y plus 1 and put it on the other side.
Okay. So probably the part you guys are most uncomfortable with there is the fraction, right? how do you get rid of the denominator of a fraction? You multiply by it. And so that's essentially what Cole's having us do. Since it's y divided by y plus 1, I'm going to multiply by y plus 1. If I multiply one side by y plus 1, multiply the other side by y plus 1. So, what is x times y plus 1? Okay, can we distribute there? Yeah, x times y. He said yx. I was going to write xy just out of habit. Plus x times 1 is x. On the other side, what's it equal? No? The y plus 1s will cancel, and we're left with y. Okay, so if we're solving for y, we're solving for y, we need all the y's together. So how can I get all the y's together? I don't want to divide the y from the x because there's another term here also, and that won't really work for me. Not exactly. I like your first step in that to get these y terms together, let's take this positive xy term that's being added on this side and subtract it to the other side. I am good with that one. So minus xy minus xy. So y minus xy is just y minus xy, and I'm flipping my sides here. And what remains on the other side? X. So I have y minus xy equals x. And I'm going to be bringing this up to finish it up. How do I separate the y out of those two terms? And the trick is because there's two terms. So I know you mentioned you wanted to divide by x. I can't divide by x because there's two terms here. Okay? How do we separate that y? Yep, that is what I want to do. Okay? Because both terms have a y, and they're not like terms I can put together or anything, let's factor a y out. So if I factor a y out on the left, what remains in parentheses? Y divided by y is going to leave me with, on the first term, y divided by y leaves me with 1 minus xy divided by y leaves me with x. So that factors to be y times 1 minus x equals, we still had an x on the other side. So how do I get the y by itself now? Now I can divide. Because I have it as two factors, a y times something else, we can divide. And because it's in parentheses, I can divide by the whole thing. Divide by 1 minus x. 1 minus x cancels. I have y equals x over 1 minus x. How do I show that's the inverse that I found? Yeah, that function, inverse function notation, f inverse of x equals x over 1 minus x. That's the hard example. Okay, there's skills that you've seen, but they're not our favorite. They're not our easiest go-to skills. Let's go ahead and do B. We'll probably skip C, just so we can make sure we have time at the end here. So, okay, on B, f of x equals the square root of 4x minus 3. What is our first step? Okay, first of all, you need to acknowledge the fact that f of x is actually y. I shortcut it, I just crossed it out there. So now if it's y equals the square root of 4x minus 3, how do I find the inverse? Switch your x's and y's. So instead of y equals, it's going to be x equals. Instead of square root of 4x minus 3, it's square root of 4y minus 3. And now I'm ready to solve for y. Okay, to get rid of that square root, we need to square both sides. And we can, because it's an equation and there's a left and a right, we can square both sides. X to the second just becomes x squared. What happens when we square that square root? Gets rid of it, and we have 4y minus 3. We now need to, how do we solve for y?
Get y minus 2, subtract 3, add 3, and then divide it.
Okay, so we'll start by adding 3. I'm going to flip it as I go here. So now I have 4y equals x squared plus 3. I told you it was. Said that first one was the hard one, right? That was a difficult one. It took some thinking. This one, is this more up your alley? Like this is more, okay, this is what you've done before. You can handle this. Okay, so now 4y divided by 4 becomes y. How should I express that y for final form? F inverse of x. And then you can do this two ways. I divided each piece by 4. You can also divide this side by 4. So I'm going to write mine as 1/4 x squared plus 3/4. However, unless there's something specific, you could also write it as x squared plus 3 all like one big fraction divided by 4. I'll take either or. Again, as I said, unless I have a reason not to. Okay, you guys okay with that stuff? C would be is more equivalent to B than A. So I was going to skip C because I figured you can figure out the steps there. Okay. Inverse reflection principle and inverse composition rule are our last two topics. Okay. The inverse reflection principle, I actually mentioned this when we were learning our 12 graphs, that a function and its inverse are symmetric across the line y equals x. And so when we say symmetric across the line y equals x, first of all, what's the line y equals x look like? Okay. That perfect diagonal line goes through 0, 0, has a slope of 1. Maybe it looks something about like that, right? That's my estimate. So I don't know if you guys remember when I was teaching those 12 functions. We had the exponential function y equals e to the x, and we had the natural log function. Those are inverses because they reflect over that diagonal line. Okay? So we're going to practice down here in a moment how you can draw an inverse. And then inverse composition rule is the other thing we're going to talk about. And this is the idea that if you have two functions, you can show that the two functions are inverses if f of g of x equals x and g of f of x equals x. So if Goff and Fogg both equal x, then that shows that those two functions you used are inverses of each other. And we will practice that down at the bottom. Okay? Key is you have to do both. You have to show Fogg and Goff to show that they are inverses. Whoops. Off the screen a little bit there, aren't I? Okay, you guys ready to try example 5? I'll give you some tips as we go as to how to draw the inverse. But example 5 asks us to sketch the graph of the inverse for the function drawn on the grid provided. So, a couple of things. First of all, remember I mentioned that it reflects over the line y equals x. So if you want, you could kind of sketch the y equals x line in there. It doesn't have to be perfect, but it gives me a visual there. I'll try and zoom mine in so you guys can see it. So that's one technique, is that we want this to be like, okay, if I take this piece of paper and I fold it, y equals x will overlap, right? That's on both sides of it. The other thing I think about is, okay, what do we know about an ordered pair and an inverse? If it was xy, or if it was ab, now it's going to be yx or ba, right? So ordered pairs will flip-flop. And we can also use that idea. So, for instance, one thing I try to do is I pick some points. If I pick this point right here that's on my original graph, what point is that? Negative 1, 0. So if that point is negative 1, 0, what's the inverse of negative 1, 0? 0, negative 1. Flip the order. So if it was 0, negative 1, it's now, I just said that wrong. If it was negative 1, 0, it's now 0, negative 1. So I'm going to put a point down there at 0, negative 1. So that's a new point I'm going to have. And I try and pick some key points like here, right here. You guys see where I'm pointing? What point is that? 0, 1. So what's the inverse of 0, 1? 1, 0. I see a point here that we could use. What point is this? 1, 2. What's the inverse of 1, 2? 2, 1. I know it kind of looks like they go in a straight line, but this is where you have to use the other things. Another key thing I can tell you is like whatever point, and I can't give you an exact point, but right here where my graph crosses that symmetric line, that y equals x, that's where my inverse is going to cross. Okay, because if it's symmetric about a line, it crosses at that same point. So right there, I'm going to have another point. Now, other than that, think about this, that it's a reflection. Okay? First of all, this point, this part of this graph right here is going down, yes? When I reflect it over here, instead of going down, it's going to fold over and it's going to go, does it make sense if I say out sideways, so to speak? It's going to go out sideways like that. And then the best thing I can think of is, okay, if you look from, say, here to here, what is my graph doing in relation to my y equals x? It's curving out and away from the line y equals x. So what's my inverse going to do on the other side? It's going to curve out and away from my line y equals x. Does that make sense? So here it curves out and away. Over here it curves out and away. In between these 2 points, do you see where I'm looking? My graph curves in toward y equals x. So if here it curves in towards y equals x, what should it be happening here? It's going to have that same, it's going to curve in towards y equals x. I don't feel like my graph is turning out very well. It turned out better this morning. Okay. And then lastly, my original graph went up. When we folded over that diagonal line, it's now going to go out to the right. Well, that might not be the best. Well, it's not horrible, I guess. I don't know. Do you see that some of the techniques I use? That's what I'm trying to show. Regardless of the end result. Pick some points, switch the x's and y's, and kind of look at, okay, I want to reflect this, so this is going out from my reflection line. This should, curve out. This is curving in towards my line. This should curve in. Pieces like that. Okay? One last thing then, and that is example 6. Example 6 gives me 2 functions, f and g. And it says to show algebraically that f and g are inverse functions. So we have to show f and g are inverse. What's true if they are inverse functions? Okay, fog and goth both equals x. So what's that mean we need to find? Fog and goth. Okay, let's worry about fog first. What's fog mean to do? Okay, so f of g of x. So that means g goes into f. Wherever there's an x, you put g into f. So let's see. F is x cubed plus 1. So when I put g in it, this x is going to be replaced with the cube root of x minus 1. So the cube root of x minus 1, then that is cubed plus 1. Does that make sense? Okay, it's not multiplication. My x is gone. But I took that g and I put it into f. Clean it up. What happens when you cube that cube root? It becomes x minus 1, and then we still have a plus 1. What's x minus 1 plus 1? X. Okay, so we showed that fog is equal to x. Now, if these are inverses of each other, it has to work both ways, which means we now have to show goth. What's goth mean? G of f of x. So that means f into g. So that means x cubed plus 1 into g. So g is the cube root of x minus 1. So it's the cube root of something minus 1. So it's the cube root of x cubed plus 1 minus 1. Clean up under the radical. X cubed plus 1 minus 1 is x cubed. What's the cube root of x cubed? X. Hey, guess what? We just showed that g and f are inverses. Okay, guys, if you haven't already started working on it, you can work now. It's page 126. Numbers 1 through 6, 9 through 12, 14 through 22 evens, and 23 to 29. 14 through 22, I forget exactly what it's asking you to do, but I am telling you, you don't have to do the domains on those.